Picture this: scattered across the vast expanse of the universe are countless tiny galaxies, each one a cosmic enigma waiting to be unraveled. These are dwarf galaxies, and while they may be small in size, they hold secrets that could rewrite our understanding of the cosmos. Did you know that for every massive galaxy like our Milky Way, there are hundreds, even thousands of these mysterious dwarf galaxies? Yet, despite their abundance, they remain some of the most puzzling objects in the universe. What makes them so strange? Why do they defy our expectations at every turn? In this video, we're diving deep into the heart of these cosmic curiosities, uncovering 30 of the most bizarre and mind-blowing discoveries about dwarf galaxies. From their unexpected role in shaping the universe to the strange phenomena lurking within them, you're about to embark on a journey that will leave you questioning everything you thought you knew about space. So, buckle up and get ready to explore the hidden wonders of these tiny but mighty galaxies. The universe has been keeping secrets, and it's time to reveal them. Now turning to our first discovery, we encounter what scientists call the missing satellite problem. Imagine running a simulation of the universe, predicting how many dwarf galaxies should be orbiting larger galaxies like our Milky Way. The results are staggering. Simulations suggest there should be hundreds, even thousands of these tiny companions. But when we look up at the night sky, we only observe a fraction of that number. Where are the rest? This puzzling discrepancy has profound implications for our understanding of dark matter and galaxy formation. Dark matter, the invisible substance that makes up most of the universe's mass, is thought to play a key role in shaping these dwarf galaxies. Yet, the fact that we don't see as many as we expect suggests that either our simulations are missing something crucial, or these galaxies are hiding in ways we don't yet understand. Could they be too faint to detect, or are they being torn apart by gravitational forces before we can spot them? This mystery not only challenges our models of the cosmos, but also pushes us to rethink how galaxies form and evolve. As we continue to explore, this missing satellite problem remains one of the most intriguing puzzles in modern astronomy. Now turning to our second discovery, we encounter the enigmatic ultra-diffuse galaxies. These ghostly giants are as large as our Milky Way, yet they contain only a tiny fraction of its stars. Picture a galaxy so faint that it barely registers against the backdrop of space. Its stars spread so thinly that it almost disappears into the void. How do such galaxies even exist? Their existence defies our expectations of how galaxies should look and behave. Typically, galaxies with such low star density would be torn apart by gravitational forces, yet these ultra-diffuse galaxies persist, challenging our understanding of star formation and galaxy evolution. What's even more fascinating is that many of these galaxies are found in galaxy clusters, where the intense gravitational environment should make their survival even more unlikely. Could they be the remnants of larger galaxies stripped of their stars over time? Or are they the result of some unique process that allows them to form and endure in such a sparse state? These faint, ghostly galaxies not only captivate our imagination, but also push us to rethink the fundamental rules of how galaxies come to be. As we continue to study them, they offer a tantalizing glimpse into the diverse and mysterious ways the universe shapes its structures. Now turning to our third discovery, we delve into the mysterious role of dark matter in dwarf galaxies. These small, faint galaxies are not just cosmic oddities, they are dominated by dark matter, making them some of the best natural laboratories for studying this elusive substance. Unlike larger galaxies, where stars and gas play a more prominent role, dwarf galaxies are often composed of up to 99% dark matter. This invisible material doesn't emit light or interact with electromagnetic forces, yet its gravitational pull is so strong that it shapes the very structure and behavior of these galaxies. Imagine a galaxy where the stars you see are just the tip of the iceberg, floating on a vast, unseen ocean of dark matter. This dominance of dark matter gives dwarf galaxies unique properties. For instance, their stars move in ways that can't be explained by the visible matter alone. Their orbits are faster and more erratic, hinting at the presence of something massive yet invisible. This makes dwarf galaxies invaluable for testing theories about dark matter and its role in the universe. What's even more intriguing is how dark matter influences the formation and evolution of these galaxies. In larger galaxies, the gravitational pull of stars and gas can sometimes mask the effects of dark matter. But in dwarf galaxies, dark matter's influence is front and center, dictating how they form, how they move, and even how they interact with their surroundings. By studying these galaxies, scientists hope to unlock the secrets of dark matter, what it's made of, how it behaves, and how it shapes the cosmos on the grandest scales. As we continue to explore these dark matter-dominated galaxies, they remind us that the universe is far more complex and mysterious than we often imagine. They challenge us to look beyond what we can see and to uncover the hidden forces that govern the cosmos. Now turning to our fourth discovery, we explore the puzzling phenomenon of star formation quenching in dwarf galaxies. Imagine a galaxy bustling with the birth of new stars, only to suddenly fall silent, as if the cosmic factory that produces stars has shut down. This is exactly what happens in some dwarf galaxies, where star formation abruptly stops, leaving behind a galaxy that grows older and dimmer over time. So, what causes this sudden halt? One leading theory points to interactions with larger galaxies. When a dwarf galaxy gets too close to a massive neighbor, the gravitational forces can strip away its gas, the raw material needed to form new stars. Without this gas, the galaxy's star-forming machinery grinds to a halt. Another possibility involves internal processes, such as supernova explosions. When massive stars explode, they can blow gas out of the galaxy, depriving it of the fuel needed to create new stars. The implications of star formation quenching are profound. It challenges our understanding of how galaxies evolve over time. In larger galaxies, star formation tends to slow down gradually, but in dwarf galaxies, it can stop abruptly, creating a stark contrast between star forming and quenched galaxies. This difference provides valuable clues about the conditions that drive or halt star formation, helping scientists piece together the complex puzzle of galaxy evolution. As we study these quenched dwarf galaxies, they remind us that the universe is full of surprises. They challenge us to rethink our assumptions and to explore the many ways galaxies can live, change, and fade over cosmic time. Now turning to our fifth discovery, we delve into the fascinating world of tidal dwarf galaxies. Unlike typical dwarf galaxies, which form from the collapse of gas clouds in the early universe, tidal dwarf galaxies are born from chaos, specifically the debris left behind after galactic collisions. Picture two massive galaxies colliding, their gravitational forces tearing each other apart and scattering gas and stars into the surrounding space. From this cosmic wreckage, new galaxies can emerge, and these are the tidal dwarf galaxies. What makes these galaxies so unique is that they challenge our traditional definitions of what a dwarf galaxy is. Typically, dwarf galaxies are thought to be ancient, small, and dominated by dark matter. But tidal dwarf galaxies are different. They are younger, often rich in gas, and may contain little to no dark matter. This is because they form from the visible matter, stars and gas, that gets flung out during galactic collisions rather than from the dark matter-dominated regions of the universe. The existence of tidal dwarf galaxies raises intriguing questions about galaxy formation and evolution. For instance, how do these galaxies survive and grow in the turbulent aftermath of a collision? And what role do they play in the larger cosmic ecosystem? By studying these galaxies, scientists gain insights into the processes that shape galaxies and the dynamic interactions that drive their evolution. As we explore tidal dwarf galaxies, we are reminded that the universe is a place of constant change and creativity. Even in the chaos of galactic collisions, new structures can emerge, offering us a glimpse into the ever-evolving story of the cosmos. Now turning to our sixth discovery, we uncover one of the most surprising revelations about dwarf galaxies, the presence of supermassive black holes. Yes, you heard that right. These small, seemingly unassuming galaxies, often overlooked in the grand tapestry of the cosmos, can harbor some of the most extreme objects in the universe. Supermassive black holes, typically associated with the centers of massive galaxies like our Milky Way, have been found lurking in the hearts of dwarf galaxies, challenging our understanding of how these cosmic giants form and evolve. So, how do supermassive black holes end up in dwarf galaxies? One theory suggests that these black holes are relics from the early universe, remnants of the first generation of massive stars that collapsed into black holes. Over time, these black holes grew, either by merging with others or by consuming surrounding gas and stars. Another possibility is that they were once part of larger galaxies that were stripped down to their cores through collisions or interactions, leaving behind a dwarf galaxy with a supermassive black hole at its center. The discovery of supermassive black holes in dwarf galaxies is more than just a cosmic curiosity, it's a window into the early universe. These black holes provide clues about the conditions that existed billions of years ago when the first galaxies were forming. By studying them, scientists can piece together how supermassive black holes grew and influenced the evolution of galaxies over cosmic time. It's like finding a fossil that tells the story of the universe's infancy. What's even more fascinating is that these black holes in dwarf galaxies might hold the key to understanding the origins of the supermassive black holes we see in larger galaxies today. Could they be the seeds from which these cosmic giants grew? The answer lies in the data, and as astronomers continue to observe and analyze these enigmatic objects, we inch closer to unraveling one of the universe's greatest mysteries. As we ponder the presence of supermassive black holes in dwarf galaxies, we are reminded that even the smallest corners of the cosmos can hold the most profound secrets. These discoveries challenge our assumptions and push the boundaries of what we thought was possible, proving once again that the universe is full of surprises. Now turning to our seventh discovery, we delve into the idea that dwarf galaxies are like cosmic fossils, preserving the conditions of the early universe. These small, ancient galaxies offer us a unique glimpse into a time when the universe was young, and the first stars and galaxies were just beginning to form. Unlike larger galaxies, which have undergone significant changes over billions of years, dwarf galaxies have remained relatively untouched, making them invaluable time capsules for astronomers. One of the most fascinating aspects of dwarf galaxies is their role in helping us understand the epoch of reionization. This was a critical period in the universe's history, occurring roughly 1 billion years after the Big Bang, when the first stars and galaxies began to emit enough light to ionize the surrounding hydrogen gas. This process transformed the universe from a dark, opaque state to the transparent cosmos we see today. Dwarf galaxies, with their simple structures and low levels of heavy elements, are thought to have played a key role in this cosmic transformation. By studying them, scientists can piece together how the first galaxies contributed to reionization and shaped the universe as we know it. What makes dwarf galaxies particularly special is their ability to preserve the chemical and physical conditions of the early universe. Many of these galaxies contain stars that formed shortly after the Big Bang, making them some of the oldest objects in the cosmos. These ancient stars have low metallicity, meaning they contain very few elements heavier than hydrogen and helium. This lack of heavy elements is a telltale sign of their age, as heavier elements were only produced later through the life cycles of stars and supernova explosions. By analyzing the light from these stars, astronomers can reconstruct the environment of the early universe and gain insights into how the first galaxies formed and evolved. Dwarf galaxies also provide clues about the nature of dark matter. which is thought to have played a crucial role in the formation of the first structures in the universe. Because dwarf galaxies are dominated by dark matter, they serve as natural laboratories for studying its properties and distribution. By observing how these galaxies move and interact, scientists can test theories about dark matter and its influence on galaxy formation. As we explore these cosmic fossils, we are reminded that the universe's history is written in the stars. Dwarf galaxies, with their ancient light and pristine conditions, offer us a rare opportunity to travel back in time and witness the dawn of the cosmos. They challenge us to rethink our understanding of galaxy formation and inspire us to keep searching for answers to the universe's deepest mysteries. Now turning to our eighth discovery, we encounter one of the most puzzling and controversial findings in modern astronomy: dwarf galaxies that appear to lack dark matter. This discovery challenges one of the fundamental pillars of our understanding of the universe, as dark matter has long been thought to be the invisible scaffolding that holds galaxies together. For decades, scientists have believed that dark matter makes up the majority of a galaxy's mass, providing the gravitational glue necessary for stars and gas to coalesce into the structures we observe. But the existence of dwarf galaxies without dark matter turns this idea on its head, forcing us to rethink how galaxies form and evolve. The first such galaxy to be identified was NGC 1052DF2, a faint, diffuse dwarf galaxy located about 65 million light-years away. Unlike typical dwarf galaxies, which are dominated by dark matter, this galaxy showed almost no signs of it. Instead, its motion and structure were entirely explained by the visible matter stars and gas within it. This finding was so unexpected that it sparked intense debate among astronomers. How could a galaxy form and survive without dark matter, and what does this mean for our understanding of the universe? One leading theory suggests that these dark matter-deficient galaxies may have formed through a different process than their dark matter-rich counterparts. For example, they could be the result of tidal interactions, where gravitational forces from a nearby larger galaxy strip away their dark matter, leaving behind only the visible components. Alternatively, they might have formed in regions of the universe where dark matter was unusually sparse, allowing stars and gas to accumulate without its influence. Whatever the explanation, these galaxies are forcing scientists to reconsider the role of dark matter in galaxy formation and to explore alternative scenarios that could account for their existence. The implications of this discovery are profound. If dark matter is not always necessary for galaxy formation, it could mean that our current models of the universe are incomplete or even incorrect. It also raises questions about the nature of dark matter itself. Is it possible that dark matter behaves differently in certain environments, or that there are different types of dark matter with varying properties? These are the kinds of questions that astronomers are now grappling with as they study these enigmatic galaxies. As we continue to explore the cosmos, dwarf galaxies with no dark matter remind us that the universe is full of surprises. They challenge our assumptions, push the boundaries of our knowledge, and inspire us to keep searching for answers. Whether they are cosmic anomalies or signs of a deeper truth, these galaxies are a testament to the complexity and mystery of the universe we inhabit. Now turning to our ninth discovery, we delve into the fascinating world of dwarf galaxies with extreme metallicity. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium, elements forged in the hearts of stars and scattered across the cosmos through supernova explosions. These heavy elements or metals play a crucial role in the formation of planets, the chemistry of life, and the evolution of galaxies. But some dwarf galaxies stand out for their unusually high or low levels of these elements, offering unique insights into the chemical history of the universe. Take, for example, dwarf galaxies with extremely low metallicity. These galaxies are like cosmic time capsules, preserving conditions similar to those in the early universe. Their stars are composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. This makes them invaluable for studying the first generations of stars, which formed when the universe was young and pristine. By analyzing these ancient stars, astronomers can piece together the story of how the first heavy elements were created and distributed, shedding light on the chemical evolution of the cosmos. On the other end of the spectrum, there are dwarf galaxies with surprisingly high metallicity. These galaxies are rich in heavy elements, often rivaling or even exceeding the metallicity of much larger galaxies like the Milky Way. How did these small galaxies accumulate so many metals? One possibility is that they experienced intense bursts of star formation, producing numerous supernovae that enriched their gas with heavy elements. Another theory suggests that they may have interacted with larger galaxies, either through collisions or by accreting metal-rich gas from their surroundings. Whatever the cause, these metal-rich dwarf galaxies challenge our understanding of how chemical enrichment occurs in the universe. The study of metallicity in dwarf galaxies also has broader implications for our understanding of galaxy formation and evolution. By comparing the metallicity of dwarf galaxies to that of larger galaxies, astronomers can trace the flow of heavy elements across cosmic time. This helps us understand how galaxies grow and evolve, and how the chemical building blocks of life are distributed throughout the universe. Visuals of metallicity maps showing the distribution of heavy elements within these galaxies provide a striking illustration of these processes, highlighting the intricate interplay between stars, gas, and the cosmic environment. As we explore these extreme metallicity dwarf galaxies, we are reminded of the incredible diversity of the universe. From ancient, metal-poor galaxies that harken back to the dawn of time, to metal-rich galaxies that defy our expectations, these cosmic laboratories continue to reveal the complex and dynamic nature of galaxy evolution. They challenge us to refine our models, expand our knowledge, and appreciate the intricate tapestry of the cosmos. Now turning to our 10th discovery, we explore how dwarf galaxies serve as powerful tools for detecting dark matter. These small, faint galaxies are not just fascinating in their own right, they are also ideal laboratories for studying one of the universe's greatest mysteries. Dark matter, which makes up about 85% of the universe's mass, does not emit, absorb, or reflect light, making it invisible to traditional telescopes. But dwarf galaxies, with their high concentrations of dark matter, provide a unique opportunity to observe its effects indirectly. One of the most promising methods for detecting dark matter involves searching for gamma rays, the highest energy form of light. According to theoretical models, dark matter particles could annihilate or decay, producing gamma rays as a byproduct. Dwarf galaxies with their dense dark matter halos are prime targets for this search. By observing these galaxies with gamma-ray telescopes, scientists hope to detect faint signals that could reveal the presence of dark matter. The search for dark matter annihilation signals is not without its challenges. Gamma rays can also be produced by other astrophysical processes, such as pulsars or supernova remnants, making it difficult to distinguish dark matter signals from background noise. To overcome this, astronomers analyze multiple dwarf galaxies, looking for consistent patterns in the gamma-ray data that could point to dark matter. This requires precise measurements and sophisticated statistical techniques, as the signals are often extremely faint. Visuals of gamma-ray telescopes, such as the Fermi Gamma-Ray Space Telescope, help illustrate the technology behind this search. These instruments scan the sky, capturing gamma rays from distant sources and providing data that scientists use to test their theories. Simulations of dark matter interactions, showing how particles might collide and produce gamma rays, further enhance our understanding of this elusive substance. The study of dwarf galaxies as dark matter detectors not only advances our knowledge of dark matter, but also deepens our understanding of galaxy formation and evolution. By mapping the distribution of dark matter in these galaxies, scientists can test theories about how galaxies grow and how dark matter shapes the large-scale structure of the universe. This research bridges the gap between the microscopic world of particle physics and the vast cosmic web, offering new insights into the fundamental nature of the universe. As we continue to probe the mysteries of dark matter through dwarf galaxies, we are reminded of the ingenuity and perseverance of scientists in their quest to understand the cosmos. These small galaxies, once overlooked, now stand at the forefront of one of the most exciting areas of modern astrophysics, shedding light on the invisible forces that shape our universe. Now turning to our 11th discovery, we uncover the fascinating phenomenon of dwarf galaxies with vast, extended dark matter halos. These halos, invisible to the naked eye, stretch far beyond the visible boundaries of the galaxies themselves, creating a gravitational framework that shapes their behavior and evolution. Unlike the compact halos seen in larger galaxies, these extended halos in dwarf galaxies challenge our understanding of how dark matter is distributed in the universe. The presence of these expansive halos has profound implications for galaxy dynamics. Dark matter, though invisible, exerts a gravitational pull that influences the motion of stars and gas within the galaxy. In dwarf galaxies with extended halos, this influence is even more pronounced as the dark matter extends far beyond the galaxy's luminous core. This creates a unique environment where the gravitational forces are dominated by dark matter rather than the visible matter we can observe. Scientists use sophisticated simulations to model these extended halos, revealing how they form and evolve over time. These simulations show that the halos are not uniform but instead have complex structures with clumps and filaments of dark matter weaving through them. Observations of dwarf galaxies combined with these simulations help astronomers map the distribution of dark matter and understand its role in shaping the universe. One of the most intriguing aspects of these extended halos is what they reveal about the nature of dark matter itself. By studying their properties, scientists can test theories about how dark matter particles interact with each other and with ordinary matter. For example, the size and shape of these halos can provide clues about the mass and velocity of dark matter particles, offering insights into the fundamental properties of this mysterious substance. Visuals of these simulations and observations bring this discovery to life, showing the intricate web of dark matter that surrounds dwarf galaxies. These images highlight the contrast between the faint, visible light of the galaxies and the vast, invisible halos that envelop them. By combining these visuals with detailed data, astronomers can piece together a more complete picture of how dark matter shapes the cosmos. The study of dwarf galaxies with extended halos not only deepens our understanding of dark matter, but also sheds light on the processes that drive galaxy formation and evolution. These galaxies serve as natural laboratories, allowing us to explore the interplay between dark matter and visible matter in ways that are impossible in larger, more complex systems. As we continue to unravel the mysteries of these extended halos, we gain new insights into the invisible forces that govern the universe, bringing us one step closer to understanding the true nature of dark matter. Now turning to our 12th discovery, we delve into the intriguing world of dwarf galaxies with unusual shapes. These galaxies defy the typical spiral or elliptical forms we often associate with larger galaxies, presenting instead with irregular, elongated, or even ring-like structures. One of the most striking examples is the polar ring galaxy, where a ring of stars, gas, and dust orbits perpendicular to the main disk of the galaxy. This peculiar arrangement challenges our understanding of how galaxies form and evolve. The formation of these unusual shapes is often the result of dramatic galactic interactions. When two galaxies pass close to one another, their gravitational forces can distort their shapes, pulling stars and gas into new configurations. In the case of polar ring galaxies, it's believed that a smaller galaxy was torn apart by the gravitational forces of a larger one, with its debris forming a ring around the host galaxy. These interactions leave behind a cosmic fingerprint, revealing the dynamic and often violent history of galactic evolution. These irregular shapes also provide valuable insights into the distribution of dark matter. The way a galaxy's shape is distorted during an interaction can reveal how dark matter is distributed within it. For example, if a galaxy's outer regions are more distorted than its core, it suggests that dark matter is more concentrated in the outer halo. By studying these shapes, astronomers can map the invisible dark matter that shapes the galaxy's structure. Visuals of these peculiar galaxies are both mesmerizing and informative. Images of polar ring galaxies with their bright rings encircling a central disk, or of irregular galaxies with chaotic, asymmetrical forms, captivate the imagination while illustrating the complex processes at work. These visuals, combined with data from telescopes and simulations, allow scientists to piece together the story of how these galaxies came to be. The study of dwarf galaxies with unusual shapes not only enriches our understanding of galactic interactions, but also highlights the diversity of the universe. These galaxies remind us that the cosmos is far from uniform, filled with unique and unexpected structures that challenge our assumptions and inspire new questions. As we continue to explore these cosmic oddities, we uncover more about the forces that shape the universe and the intricate dance of matter and gravity that defines it. Now turning to our 13th discovery, we explore the fascinating phenomenon of dwarf galaxies hosting active galactic nuclei, or AN. These AGN are incredibly energetic regions at the center of galaxies, powered by supermassive black holes that devour surrounding matter, releasing vast amounts of energy in the process. While AGN are more commonly associated with massive galaxies, their presence in dwarf galaxies is both surprising and enlightening, offering new insights into the early universe and the evolution of galaxies. The formation of AGN in dwarf galaxies challenges our understanding of how supermassive black holes grow. In larger galaxies, these black holes are thought to form through mergers and the accumulation of gas over billions of years. But in dwarf galaxies, which are smaller and less massive, the presence of AGN suggests that supermassive black holes can form and grow even in environments with fewer resources. This raises intriguing questions about the conditions required for black hole formation and the role of dwarf galaxies in the cosmic timeline. The impact of AGN on dwarf galaxies is profound. The intense radiation and powerful jets emitted by AGN can heat up and expel gas from the galaxy, effectively quenching star formation. This process, known as feedback, plays a crucial role in shaping the evolution of galaxies. In larger galaxies, AGN feedback is a well-studied phenomenon, but in dwarf galaxies, its effects are even more dramatic due to their smaller size and lower gravitational pull. By studying AGN in dwarf galaxies, astronomers can better understand how feedback influences galaxy growth and star formation across the universe. Visuals of AGN activity in dwarf galaxies are both striking and informative. Images captured by telescopes reveal bright, energetic cores surrounded by faint, diffuse light from the host galaxy. These visuals, combined with data from radio, X-ray, and infrared observations, allow scientists to map the structure and behavior of AGN in unprecedented detail. Comparisons to AGN in larger galaxies highlight the differences in scale and intensity, providing a clearer picture of how these cosmic engines operate across a range of environments. The discovery of AGN in dwarf galaxies not only expands our knowledge of black hole formation and galaxy evolution, but also underscores the diversity of the universe. These small yet powerful galaxies remind us that even the most unassuming corners of the cosmos can harbor extraordinary phenomena. As we continue to study these active galactic nuclei, we uncover new clues about the forces that shape galaxies and the intricate interplay between black holes, gas, and stars that drives the evolution of the universe. Now turning to our 14th discovery, we delve into the role of dwarf galaxies as probes of cosmic reionization, a pivotal era in the history of the universe. Cosmic reionization marks the period when the first stars and galaxies formed, emitting intense ultraviolet light that ionized the surrounding hydrogen gas, transforming the universe from a dark, opaque state to the transparent cosmos we observe today. Dwarf galaxies, with their small size and relatively simple structures, are thought to have played a crucial role in this process, making them invaluable tools for studying this transformative epoch. The challenge, however, lies in observing these ancient dwarf galaxies. Due to their faintness and the vast distances involved, detecting them requires cutting-edge telescopes and innovative observational techniques. Astronomers rely on deep-field surveys and advanced instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope to peer back in time and capture the faint glow of these early galaxies. Visuals from these observations reveal a patchwork of young, star-forming dwarf galaxies scattered across the early universe, their light stretched and redshifted by the expansion of space. Simulations of cosmic reionization further illuminate the role of dwarf galaxies. These models show how the first dwarf galaxies, though small, collectively produced enough ultraviolet radiation to ionize the surrounding hydrogen gas. By comparing these simulations with observational data, scientists can refine their understanding of how reionization unfolded and the specific contributions of dwarf galaxies. Visuals of these simulations often depict a cosmic web of ionized bubbles growing and merging, driven by the energetic output of countless dwarf galaxies. The study of dwarf galaxies as probes of reionization not only sheds light on the early universe but also helps us understand the formation and evolution of larger galaxies. These small galaxies acted as cosmic seeds, their ionizing radiation paving the way for the growth of more complex structures. By unraveling the mysteries of reionization, astronomers gain deeper insights into the forces that shaped the universe and set the stage for the rich tapestry of galaxies we see today. As we continue to explore these ancient dwarf galaxies, we uncover new chapters in the story of our cosmic origins. Now turning to our 15th discovery, we explore the fascinating phenomenon of dwarf galaxies with multiple stellar populations. Unlike many galaxies that host stars of similar ages and compositions, these dwarf galaxies contain stars that vary dramatically in both age and chemical makeup. This diversity offers a unique window into the complex history of galaxy formation and evolution. The presence of multiple stellar populations suggests that these dwarf galaxies have undergone several distinct episodes of star formation. Some stars may have formed early in the galaxy's history, while others were born much later, possibly triggered by interactions with neighboring galaxies or internal processes like gas accretion. Visuals of stellar population maps reveal a patchwork of colors and brightness, each representing stars of different ages and compositions, painting a vivid picture of the galaxy's dynamic past. One of the most intriguing aspects of these galaxies is what their stellar populations reveal about their environments. Older stars, often rich in elements like hydrogen and helium, hint at the pristine conditions of the early universe. In contrast, younger stars, which contain heavier elements forged in previous generations of stars, tell a story of ongoing chemical enrichment. By studying these populations, astronomers can piece together the timeline of star formation and the processes that shape the galaxy over billions of years. Comparisons between dwarf galaxies with single and multiple stellar populations further highlight their significance. Galaxies with uniform stellar populations often indicate a quieter history, with star formation occurring in a single, concentrated burst. In contrast, those with multiple populations suggest a more turbulent past, marked by repeated interactions and bursts of activity. Visuals comparing these galaxies side by side emphasize the stark differences in their histories and the richness of the stories they tell. The study of dwarf galaxies with multiple stellar populations not only deepens our understanding of these small but complex systems, but also provides insights into the broader processes of galaxy evolution. By unraveling the histories of these galaxies, we gain a clearer picture of how the universe's smallest structures grow and change over time. As we continue to explore these cosmic time capsules, we uncover new layers of the universe's intricate and ever-evolving story. Now turning to our 16th discovery, we delve into the peculiar world of dwarf galaxies with unusual kinematics. These galaxies exhibit strange motion patterns, such as stars that rotate in opposite directions or chaotic orbits that defy expectations. These bizarre behaviors challenge our understanding of how galaxies move and evolve, offering a fascinating glimpse into the complexities of cosmic dynamics. The formation of these unusual kinematics often stems from dramatic events in a galaxy's history. For instance, counter-rotating stars may arise from galactic collisions or mergers, where two galaxies with opposite rotational directions combine, leaving behind a mixed population of stars moving in conflicting ways. Chaotic orbits, on the other hand, can result from gravitational interactions with neighboring galaxies or the influence of dark matter halos, which can disrupt the orderly motion of stars within a galaxy. Visuals of kinematic maps reveal these strange patterns in stunning detail. Imagine a galaxy where some stars spiral clockwise while others move counterclockwise, or where stars follow erratic, unpredictable paths. These maps not only highlight the peculiar motions but also provide clues about the forces at play, such as the distribution of dark matter or the remnants of past interactions. Simulations further bring these dynamics to life, showing how galaxies evolve over time under the influence of these chaotic forces. The implications of these unusual kinematics are profound. They challenge traditional models of galaxy formation, which often assume orderly, predictable motions. Instead, they suggest that dwarf galaxies are far more dynamic and complex than previously thought. By studying these galaxies, astronomers can refine their understanding of how gravitational forces, dark matter, and galactic interactions shape the universe's smallest structures. Comparisons between dwarf galaxies with typical and unusual kinematics further underscore their significance. While most galaxies exhibit smooth, coherent motions, those with strange kinematics reveal the turbulent histories and external influences that have shaped them. Visuals comparing these galaxies side by side emphasize the stark differences in their dynamics and the stories they tell about their past. The study of dwarf galaxies with unusual kinematics not only deepens our understanding of these enigmatic systems, but also sheds light on the broader processes that govern galaxy evolution. As we continue to explore these cosmic oddities, we uncover new layers of complexity in the universe's smallest and most intriguing structures. Now turning to our 17th discovery, we explore how dwarf galaxies serve as prime candidates for detecting dark matter annihilation signals. These small, faint galaxies are rich in dark matter, making them ideal laboratories for studying this elusive substance. The search for dark matter annihilation signals focuses on detecting gamma rays, which are thought to be produced when dark matter particles collide and annihilate each other. Dwarf galaxies, with their high concentrations of dark matter and relatively low levels of background radiation, provide a clean environment for this search. Astronomers use advanced gamma-ray telescopes, such as the Fermi Gamma Ray Space Telescope, to scan dwarf galaxies for these elusive signals. Visuals of these telescopes in action, combined with simulations of dark matter interactions, help illustrate the process. Imagine a galaxy surrounded by a faint glow of gamma rays, the telltale sign of dark matter annihilation. These observations are painstakingly analyzed to distinguish potential signals from other sources of gamma rays, such as pulsars or cosmic rays. The significance of detecting dark matter annihilation in dwarf galaxies cannot be overstated. Such a discovery would provide direct evidence for the existence of dark matter, a substance that makes up about 85% of the universe's mass but has never been directly observed. It would also offer insights into the properties of dark matter particles, such as their mass and how they interact with each other. This knowledge could revolutionize our understanding of the universe's composition and the fundamental forces that govern it. Visuals of detection techniques and simulations play a crucial role in conveying the complexity of this search. For instance, animations might show how gamma rays are produced during dark matter annihilation and how telescopes capture these signals. Comparisons between observed gamma ray data and theoretical predictions highlight the challenges and excitement of this scientific endeavor. The study of dwarf galaxies as dark matter annihilation sites not only advances our quest to understand dark matter, but also underscores the importance of these small galaxies in unraveling the universe's greatest mysteries. As we continue to probe their depths, we edge closer to answering one of the most profound questions in modern astrophysics. What is dark matter and how does it shape the cosmos? Now turning to our 18th discovery, we delve into the fascinating world of dwarf galaxies with extreme star formation rates. These galaxies are cosmic powerhouses undergoing bursts of rapid star formation that defy expectations. Imagine a galaxy suddenly igniting with the birth of thousands, even millions of new stars in a relatively short period of time. This phenomenon, known as a starburst, transforms these small galaxies into dazzling beacons of light and energy. But what triggers these explosive bursts of star formation? One major factor is galactic interactions. When dwarf galaxies collide or pass close to larger galaxies, the gravitational forces can compress gas clouds, igniting a frenzy of star birth. Another trigger could be internal processes, such as the sudden collapse of massive gas clouds within the galaxy itself. Visuals of these star-forming regions, glowing with the light of newborn stars, help illustrate the intensity of these events. The impact of extreme star formation on galaxy evolution is profound. These bursts can dramatically alter a dwarf galaxy's structure, chemistry, and future. For instance, the rapid formation of massive stars leads to supernova explosions, which enrich the galaxy with heavy elements and can trigger further star formation. However, these same supernova can also blow away gas and dust, potentially quenching future star formation and leaving the galaxy quieter and more stable. Comparisons between starburst dwarf galaxies and their more tranquil counterparts highlight the stark differences in their evolution. Visuals might show a galaxy ablaze with star-forming regions next to one with a calm, steady rate of star birth. These contrasts help us understand how extreme star formation shapes the life cycle of galaxies. As we explore these cosmic fireworks, we gain deeper insights into the dynamic processes that drive galaxy evolution. Dwarf galaxies with extreme star formation rates remind us that even the smallest galaxies can play a dramatic role in the story of the universe. With each burst of star formation, they leave an indelible mark on the cosmos, challenging our understanding of how galaxies grow and change over time. Now turning to our 19th discovery, we explore dwarf galaxies with unusual gas content, a phenomenon that challenges our understanding of how these small cosmic systems function. Gas, primarily hydrogen, is the lifeblood of star formation, and its distribution and quantity within a galaxy can dramatically influence its evolution. But some dwarf galaxies defy expectations, harboring gas in amounts or patterns that seem to break the rules. In some cases, dwarf galaxies are found with far more gas than their size would suggest. These gas-rich galaxies are like cosmic reservoirs, holding vast amounts of raw material for future star formation. But why do they have so much gas? One possibility is that they have avoided interactions with larger galaxies, which can strip away gas through gravitational forces. Another explanation could be that they are still in the early stages of their evolution, having not yet used up their gas reserves to form stars. Visuals of these galaxies, with their glowing gas clouds stretching far beyond their stellar boundaries, help illustrate their unique nature. On the other hand, some dwarf galaxies have surprisingly little gas despite their small size. These gas-poor galaxies are often found in dense environments such as galaxy clusters, where interactions with other galaxies or the cluster's hot gas can strip away their gas supply. Without gas, these galaxies struggle to form new stars, leaving them dim and quiet. Visuals might show a gas-poor dwarf galaxy, its stars sparse and faint, compared to a gas-rich counterpart teeming with glowing clouds and young stars. The unusual gas content in these galaxies has profound implications for their star formation and overall dynamics. In gas-rich galaxies, the abundance of fuel can lead to bursts of star formation, creating dazzling regions of newborn stars. However, in gas-poor galaxies, the lack of material can halt star formation entirely, leaving them in a state of cosmic dormancy. These extremes highlight the delicate balance between gas supply and star formation, and how even small changes can dramatically alter a galaxy's fate. By studying these galaxies, astronomers gain valuable insights into the processes that shape galaxy evolution. Dwarf galaxies with unusual gas content serve as cosmic laboratories, revealing how gas flows, interactions, and environmental factors influence the life cycle of galaxies. As we continue to explore these enigmatic systems, we uncover new layers of complexity in the story of the universe, reminding us that even the smallest galaxies hold secrets waiting to be discovered. Now turning to our 20th discovery, we delve into the fascinating concept of dwarf galaxies as relics of galactic cannibalism. These galaxies are not born small. Instead, they are the remnants of larger galaxies that have been torn apart by intense gravitational interactions. Imagine a cosmic tug-of-war, where the immense gravitational forces of a larger galaxy pull apart a smaller one, leaving behind fragments that eventually evolve into dwarf galaxies. These remnants carry the scars of their violent past, offering astronomers a unique window into the chaotic processes that shape the universe. What makes these dwarf galaxies so intriguing is their unique properties. Unlike typical dwarf galaxies that form independently, these relics often retain traces of their original structure, such as streams of stars and gas that stretch across space. These tidal streams, as they are called, are like cosmic breadcrumbs marking the path of the galaxy's destruction. Visuals of these streams, glowing faintly against the dark backdrop of space, help illustrate the dramatic history of these galaxies. They are not just remnants, they are storytellers preserving the tale of their demise. The study of these dwarf galaxies reveals crucial insights into galactic evolution. By analyzing their composition and structure, astronomers can piece together the events that led to their formation. For instance, the presence of older stars and unusual chemical abundances in these galaxies suggests they were once part of much larger systems. This information helps us understand how galaxies grow, interact, and evolve over time. Galactic cannibalism is not just a destructive process, it is also a creative one, giving rise to new forms of galaxies that continue to shape the cosmic landscape. Moreover, these dwarf galaxies challenge our understanding of galaxy formation. They remind us that the universe is a dynamic and ever-changing place, where even the largest structures are not immune to the forces of gravity. By studying these relics, we gain a deeper appreciation for the complexity of galactic interactions and the delicate balance that governs the cosmos. As we continue to explore these remnants of galactic cannibalism, we uncover new layers of the universe's history, revealing how even destruction can lead to creation. Now turning to our 21st discovery, we explore the intriguing world of dwarf galaxies with exotic stellar populations. These galaxies are home to some of the rarest and most fascinating stars in the universe, such as blue stragglers and hypervelocity stars. Blue stragglers, for instance, are stars that appear younger and hotter than their neighbors, defying the typical aging process of stellar populations. They are thought to form through stellar collisions or the transfer of material between stars in binary systems, creating a cosmic anomaly that challenges our understanding of star evolution. Hypervelocity stars, on the other hand, are stars that move at incredible speeds, often so fast that they can escape the gravitational pull of their host galaxy. These stars are believed to be launched by interactions with supermassive black holes or through the explosive disruption of binary star systems. Visuals of these stars streaking across the galaxy, leaving trails of light in their wake, help illustrate their extraordinary nature. They are like cosmic outlaws, breaking free from the confines of their galactic homes and venturing into the vastness of intergalactic space. The presence of these exotic stars in dwarf galaxies provides valuable insights into the dynamic processes at work in these small but complex systems. Blue stragglers, for example, offer clues about the density and interactions of stars in crowded galactic environments, while hypervelocity stars shed light on the gravitational forces that shape galaxies. By studying these rare stellar populations, astronomers can piece together the history and evolution of dwarf galaxies, revealing how they form, interact, and change over time. Moreover, these stars challenge our understanding of stellar physics and galactic dynamics. They remind us that even the smallest galaxies can host some of the most extreme and unusual phenomena in the universe. As we continue to explore these dwarf galaxies with exotic stellar populations, we uncover new layers of complexity in the cosmos, deepening our appreciation for the diversity and wonder of the universe. These stars are not just anomalies, they are windows into the extraordinary processes that shape the galaxies we see today. Now turning to our 22nd discovery, we delve into the fascinating world of dwarf galaxies with unusual magnetic fields. These galaxies, often overlooked due to their small size, harbor magnetic fields that are surprisingly strong or exhibit peculiar patterns, challenging our understanding of galactic dynamics. Magnetic fields in galaxies are typically generated by the motion of charged particles, such as electrons and protons, as they spiral around magnetic field lines. However, in dwarf galaxies, these fields can take on unique characteristics, often amplified by intense star formation or interactions with neighboring galaxies. The formation of these unusual magnetic fields is still a topic of active research. One leading theory suggests that they are generated by turbulent gas flows within the galaxy, driven by supernova explosions or the collision of gas clouds. These processes can amplify magnetic fields to levels far beyond what is seen in larger galaxies. Another possibility is that these fields are remnants of earlier galactic interactions, where the gravitational pull of a passing galaxy twisted and stretched the magnetic field lines, leaving behind a complex and irregular pattern. The impact of these magnetic fields on galaxy dynamics is profound. They can influence the motion of gas and dust, shaping the formation of stars and even the structure of the galaxy itself. In some cases, strong magnetic fields can suppress star formation by preventing gas clouds from collapsing, while in others, they can channel gas into dense regions, triggering bursts of star formation. Visuals of magnetic field maps and simulations help illustrate these processes, showing how the invisible forces of magnetism shape the visible structure of dwarf galaxies. Studying these unusual magnetic fields provides valuable insights into the physical processes that govern galaxy evolution. They reveal how even the smallest galaxies can exhibit complex and dynamic behavior, driven by forces that are often hidden from view. As we continue to explore these magnetic mysteries, we gain a deeper understanding of the intricate interplay between magnetism, gravity, and star formation in the cosmos. These dwarf galaxies, with their peculiar magnetic fields, remind us that the universe is full of surprises, waiting to be uncovered by the curious minds of astronomers. Now turning to our 23rd discovery, we explore how dwarf galaxies serve as invaluable probes for studying galactic winds and their role in shaping galaxy evolution. Galactic winds, powerful streams of gas and dust ejected from galaxies, play a crucial role in regulating star formation and redistributing matter across the cosmos. These winds are driven by intense processes such as supernova explosions, stellar radiation, and the activity of supermassive black holes. However, observing these winds in larger galaxies can be challenging due to their complex environments and the sheer scale of the phenomena. This is where dwarf galaxies come into play. Dwarf galaxies, with their simpler structures and lower masses, provide a clearer window into the mechanisms of galactic winds. Their smaller size and less chaotic environments make it easier to trace the origins and impacts of these winds. For instance, in dwarf galaxies, winds often originate from concentrated bursts of star formation, allowing astronomers to study how these outflows interact with the surrounding gas and influence future star formation. Visuals of wind simulations and observations show how these winds can sweep through a galaxy, carrying away material and altering its chemical composition. One of the key challenges in studying galactic winds in dwarf galaxies is their faintness. The winds, often composed of ionized gas, emit light that is difficult to detect against the backdrop of the galaxy itself. Advanced telescopes and spectroscopic techniques are required to isolate and analyze these faint signals. Despite these challenges, the insights gained are profound. By studying galactic winds in dwarf galaxies, astronomers can better understand how these outflows regulate the growth of galaxies, enrich the intergalactic medium with heavy elements, and even influence the formation of future generations of stars. The significance of these findings extends beyond dwarf galaxies. Galactic winds are a universal phenomenon occurring in galaxies of all sizes and shapes. By studying them in dwarf galaxies, we gain a clearer picture of how they operate in more complex systems, including our own Milky Way. These observations also shed light on the feedback processes that balance star formation and galaxy growth, ensuring that galaxies do not consume all their gas too quickly. As we continue to probe the mysteries of galactic winds through the lens of dwarf galaxies, we uncover new layers of understanding about the forces that shape the universe. These small but mighty galaxies remind us that even the faintest whispers of the cosmos can carry profound insights, waiting to be heard by those who listen closely. Now turning to our 24th discovery, we delve into the fascinating world of dwarf galaxies with unusual chemical abundances. These galaxies, often overlooked due to their small size, hold secrets about the chemical evolution of the universe that challenge our understanding of galactic history. Unlike larger galaxies, which tend to have more uniform chemical compositions, dwarf galaxies can exhibit surprising variations in their elemental makeup, offering a unique window into the processes that shape the cosmos. The chemical composition of a galaxy is like a cosmic fingerprint, revealing the history of star formation, supernova explosions, and even interactions with other galaxies. In dwarf galaxies, astronomers have found some with unexpectedly high levels of heavy elements such as iron and oxygen, while others are surprisingly deficient in these elements. These anomalies are not just random quirks, they tell a story about the galaxy's past. For instance, a dwarf galaxy with an abundance of heavy elements might have experienced intense bursts of star formation, where massive stars lived fast, died young, and enriched their surroundings with the elements forged in their cores. On the other hand, a galaxy with low metallicity might be a relic from the early universe, preserving conditions similar to those just after the Big Bang. One of the most intriguing aspects of these unusual chemical abundances is what they reveal about galactic interactions. When dwarf galaxies collide or interact with larger galaxies, they can exchange gas and dust, altering their chemical makeup. These interactions can trigger new waves of star formation, further complicating the chemical signature of the galaxy. Visuals of chemical abundance maps show these variations in vivid detail, highlighting regions rich in certain elements and others that are surprisingly barren. These maps are like cosmic treasure charts, guiding astronomers to the most interesting and informative parts of the galaxy. Studying these chemical anomalies also helps us understand the broader processes of galactic evolution. For example, the presence of certain elements can indicate the types of stars that once existed in the galaxy, while the absence of others might suggest a lack of recent star formation. By comparing the chemical compositions of different dwarf galaxies, astronomers can piece together a timeline of how galaxies grow and change over billions of years. These comparisons also shed light on the role of dwarf galaxies in the cosmic ecosystem, as they contribute heavy elements to the intergalactic medium through winds and outflows. The implications of these discoveries extend far beyond dwarf galaxies themselves. By understanding how chemical abundances vary in these small systems, we gain insights into the processes that shaped larger galaxies, including our own Milky Way. These findings remind us that even the smallest galaxies can hold the keys to unlocking some of the universe's greatest mysteries. As we continue to explore these chemical oddities, we uncover new layers of understanding about the forces that have shaped the cosmos from its earliest moments to the present day. Now turning to our 25th discovery, we explore how dwarf galaxies serve as invaluable tracers of the large-scale structure of the universe. These small, often faint galaxies are like cosmic signposts, helping astronomers map the intricate web of matter that stretches across the cosmos. Known as the cosmic web, this vast network of filaments, voids, and clusters forms the backbone of the universe, and dwarf galaxies play a crucial role in revealing its hidden architecture. The cosmic web is a product of the universe's evolution, shaped by the gravitational pull of dark matter and the expansion of space itself. Dwarf galaxies, being abundant and widely distributed, act as natural markers for this structure. Because they are less likely to be influenced by the complex dynamics of larger galaxies, their positions and movements provide a clearer picture of the underlying distribution of matter. By studying the locations and velocities of dwarf galaxies, astronomers can trace the filaments of the cosmic web, identifying where matter is concentrated and where vast voids lie. One of the most striking aspects of this discovery is how dwarf galaxies help us understand the formation and growth of the cosmic web. In the early universe, tiny fluctuations in density gave rise to the first structures, which grew over billions of years into the web we see today. Dwarf galaxies, often found in the outskirts of these filaments or near the edges of voids, offer clues about how these structures evolved. Their distribution and properties can reveal the history of gravitational interactions, mergers, and the flow of gas and dark matter that shaped the universe on the largest scales. Visuals of large-scale structure maps and simulations bring this concept to life, showing the intricate connections between dwarf galaxies and the cosmic web. These maps highlight how dwarf galaxies are not randomly scattered, but instead align with the filaments and nodes of the web, tracing its contours with remarkable precision. Simulations, on the other hand, allow us to rewind the clock, showing how these galaxies formed and moved over time, painting a dynamic picture of the universe's growth. The role of dwarf galaxies in mapping the cosmic web also has profound implications for our understanding of dark matter and dark energy. Since dark matter makes up the majority of the cosmic web's mass, the distribution of dwarf galaxies helps us infer where this invisible substance lies. Additionally, by studying how the positions of dwarf galaxies change over time, astronomers can probe the effects of dark energy, the mysterious force driving the accelerated expansion of the universe. This discovery underscores the importance of dwarf galaxies as cosmic tools, offering insights into the universe's structure and evolution that larger galaxies alone cannot provide. As we continue to map the cosmic web using these small but mighty galaxies, we gain a deeper understanding of the forces that have shaped the universe from its earliest moments to the present day. With each new observation, we uncover more about the grand tapestry of the cosmos, revealing the intricate connections that bind everything together. Now turning to our 26th discovery, we explore dwarf galaxies that host some of the most unusual star clusters in the universe. Among these are ultra-compact dwarfs, dense collections of stars that defy our expectations of what star clusters should look like. These peculiar clusters are not only fascinating in their own right, but also provide critical insights into the processes that shape galaxies. Ultra-compact dwarfs are incredibly dense, packing hundreds of thousands of stars into a region just a few hundred light-years across. To put that in perspective, imagine squeezing the entire population of stars in a typical globular cluster into a space 1/10 the size. This extreme density makes them stand out, even among the already diverse family of dwarf galaxies. But how do these ultra-compact dwarfs form? One leading theory suggests they are the remnants of larger galaxies that were stripped of their outer layers during violent interactions with other galaxies. Over time, gravitational forces compress the remaining core into a tight, compact structure, creating these unique star clusters. The significance of these unusual star clusters goes beyond their formation. They serve as cosmic laboratories, allowing astronomers to study the effects of extreme gravitational environments on star formation and evolution. For example, the high density of stars in ultra-compact dwarfs can lead to frequent stellar collisions, which may produce exotic objects like blue stragglers or even black holes. By studying these clusters, scientists can gain a better understanding of how stars behave under conditions that are impossible to replicate on Earth. Visuals of these star clusters and their host galaxies reveal their striking appearance. Ultra-compact dwarfs often appear as tiny, bright dots nestled within the faint glow of their parent dwarf galaxies. These images highlight the contrast between the dense clusters and the more diffuse background of the galaxy, emphasizing their unique nature. Simulations, on the other hand, show the dynamic processes that lead to their formation, from the initial galactic collision to the final compression into an ultra-compact dwarf. The discovery of these unusual star clusters also has broader implications for our understanding of galaxy evolution. They challenge traditional classifications of star clusters and dwarf galaxies, blurring the lines between the two. This forces astronomers to rethink how they categorize and study these objects, leading to new insights into the diversity of structures in the universe. Additionally, the presence of ultra-compact dwarfs in dwarf galaxies suggests that even the smallest galaxies can undergo dramatic transformations, driven by interactions with their cosmic neighbors. As we continue to study these remarkable star clusters, we uncover more about the complex processes that shape the universe, from their formation in the aftermath of galactic collisions to their role as cosmic laboratories. Ultra-compact dwarfs and other unusual star clusters offer a window into the dynamic and ever-changing nature of the cosmos. With each new observation, we gain a deeper appreciation for the incredible diversity of structures that exist in the universe, reminding us that even the smallest galaxies can hold the biggest surprises. Now turning to our 27th discovery, we delve into how dwarf galaxies serve as powerful tools for studying one of the most mysterious forces in the universe, dark energy. This enigmatic force is believed to be driving the accelerated expansion of the cosmos, and dwarf galaxies, with their unique properties, provide a unique window into understanding its effects. To study dark energy, astronomers often rely on observations of distant dwarf galaxies. These galaxies act as cosmic mile markers, helping scientists measure the rate at which the universe is expanding. By analyzing the light from these galaxies, researchers can determine their distance and how fast they are moving away from us. This information is crucial for mapping the expansion history of the universe and uncovering the influence of dark energy. One of the primary methods used involves observing Type 1, a supernova within dwarf galaxies. These supernovae, often referred to as standard candles, have a consistent brightness, making them ideal for measuring cosmic distances. By comparing the observed brightness of these supernovae to their known intrinsic brightness, astronomers can calculate how far away they are. Over time, tracking these distances across different epochs of the universe reveals how the expansion rate has changed, offering clues about the nature of dark energy. However, studying dark energy through dwarf galaxies is not without its challenges. These galaxies are often faint and located at great distances, making them difficult to observe in detail. Additionally, the presence of cosmic dust and other interstellar material can obscure their light, complicating measurements. To overcome these obstacles, astronomers use advanced telescopes and instruments, such as the Hubble Space Telescope and upcoming missions like the Nancy Grace Roman Space Telescope, which are designed to capture faint light from distant galaxies with unprecedented precision. Visuals of dark energy simulations and observations play a crucial role in this research. Simulations show how dark energy influences the large-scale structure of the universe, causing galaxies to move apart at an accelerating rate. Observations, on the other hand, provide real-world data that validate these models. For example, maps of the cosmic web, created using data from dwarf galaxies, reveal the intricate network of filaments and voids shaped by dark energy over billions of years. The study of dwarf galaxies as probes of dark energy not only deepens our understanding of this mysterious force, but also sheds light on the ultimate fate of the universe. Will the expansion continue to accelerate indefinitely, or could dark energy evolve in unexpected ways? These are questions that dwarf galaxies, with their unique role in cosmic history, are helping us answer. As we continue to explore these small but mighty galaxies, we move closer to unraveling one of the greatest mysteries of the cosmos. Now turning to our 28th discovery, we explore the fascinating world of dwarf galaxies undergoing unusual interactions, such as collisions and mergers. These cosmic encounters, though often chaotic, play a crucial role in shaping the evolution of galaxies, offering a glimpse into the dynamic processes that drive the universe. Dwarf galaxies, despite their small size, are not isolated in the vastness of space. They frequently interact with other galaxies, including larger ones, through gravitational forces. These interactions can take many forms, from gentle tidal pulls to dramatic collisions that reshape their structures. When two dwarf galaxies collide, the result is often a burst of star formation, as the gravitational forces compress gas and dust, igniting the birth of new stars. These starbursts can transform the appearance and composition of the galaxies involved, leaving behind a trail of bright, young stars and glowing gas clouds. One of the most intriguing aspects of these interactions is how they influence the evolution of dwarf galaxies. In some cases, collisions can strip away gas and dust, leaving the galaxies unable to form new stars. This process, known as star formation quenching, can turn a once-active galaxy into a quiet, aging relic. In other cases, mergers can lead to the creation of entirely new structures, such as tidal dwarf galaxies, which form from the debris of the collision. These galaxies, born from chaos, often have unique properties that challenge our traditional understanding of galaxy formation. Visuals of these interactions are both stunning and informative. Simulations show the intricate dance of galaxies as they approach each other, their shapes distorted by gravitational forces. Observations, on the other hand, capture the aftermath of these cosmic encounters, revealing the bright knots of star formation and the twisted streams of gas and stars left behind. For example, the Antennae galaxies, a pair of colliding galaxies, provide a real-world example of how such interactions can transform galaxies on a grand scale. Understanding these unusual interactions is not just about observing the chaos, it's about uncovering the underlying processes that drive galaxy evolution. By studying how dwarf galaxies interact, astronomers can piece together the history of galaxy formation and gain insights into the forces that shape the universe. These interactions also provide clues about the role of dark matter, as the gravitational effects of these unseen particles influence the outcomes of collisions and mergers. As we continue to explore the strange and dynamic interactions of dwarf galaxies, we uncover new layers of complexity in the cosmic tapestry. These small but mighty galaxies, through their collisions and mergers, remind us that even in the vastness of space, no galaxy is an island. Their interactions shape not only their own destinies, but also the broader story of the universe itself. Now turning to our 29th discovery, we delve into how dwarf galaxies serve as powerful probes for studying galactic feedback processes. Galactic feedback refers to the mechanisms by which energy and matter are expelled from a galaxy, often driven by events like supernova explosions or the activity of supermassive black holes. These processes play a critical role in regulating star formation and shaping the evolution of galaxies, and dwarf galaxies, with their simpler structures, provide a unique window into understanding these phenomena. In dwarf galaxies, supernova explosions are one of the primary drivers of galactic feedback. When massive stars reach the end of their lives, they explode in spectacular supernova, releasing enormous amounts of energy and ejecting material into the surrounding space. This energy can heat up the gas within the galaxy, preventing it from cooling and collapsing to form new stars. In this way, supernova act as a kind of cosmic thermostat, regulating the rate at which stars are born. Without this feedback, dwarf galaxies might form stars at a much faster pace, leading to very different evolutionary outcomes. But supernova aren't the only source of feedback. In some dwarf galaxies, the presence of active galactic nuclei, or AN, can also drive feedback processes. Although AGN are more commonly associated with larger galaxies, their presence in dwarf galaxies has been a surprising discovery. The energy emitted by these AGN can push gas out of the galaxy, further quenching star formation and altering the galaxy's structure. This interplay between star formation and feedback creates a delicate balance that determines the fate of a galaxy. Visuals of these feedback processes are both dramatic and enlightening. Simulations show the shockwaves from supernova explosions rippling through the gas clouds of dwarf galaxies, dispersing material and heating the surrounding environment. Observations, on the other hand, capture the glowing remnants of supernova and the faint outflows of gas being driven by AGN activity. For example, the dwarf galaxy NGC 1569, with its intense star-forming regions and visible supernova remnants, offers a real-world glimpse into how feedback shapes a galaxy's evolution. Studying feedback in dwarf galaxies is not just about understanding these small systems. It's about gaining insights into the broader mechanisms that govern all galaxies. Dwarf galaxies, with their relatively simple structures and lower gravitational pull, allow astronomers to isolate and study feedback processes in ways that are often impossible in larger, more complex galaxies. By observing how feedback regulates star formation in dwarf galaxies, scientists can refine their models of galaxy evolution and better understand the forces that shape the universe. As we explore the role of dwarf galaxies as probes of galactic feedback, we uncover the intricate balance between creation and destruction in the cosmos. These small galaxies, through their supernova and AGN activity, remind us that even the smallest systems can have a profound impact on the grand story of the universe. Their feedback processes not only shape their own destinies, but also provide crucial clues about the evolution of galaxies on a much larger scale. Now turning to our 30th and final discovery, we explore dwarf galaxies with unusual luminosity functions. Luminosity functions describe how stars of different brightness levels are distributed within a galaxy, and in dwarf galaxies, these distributions can sometimes defy expectations. These unexpected patterns in star brightness offer fascinating insights into the processes that shape galaxies and the history of star formation within them. In typical galaxies, the luminosity function follows a predictable pattern, with a large number of dim stars and fewer bright ones. However, some dwarf galaxies show deviations from this norm, with an overabundance of either very bright or very faint stars. These anomalies can be traced back to unique events in the galaxy's past, such as bursts of rapid star formation or the influence of external forces like gravitational interactions with neighboring galaxies. For example, a sudden influx of gas might trigger a wave of star formation, leading to an unusual number of bright, young stars. Conversely, the loss of gas due to galactic winds or collisions could leave a galaxy dominated by older, dimmer stars. One striking example of this phenomenon can be seen in the dwarf galaxy Leo A. This galaxy, located about 2.5 million light-years from Earth, has a luminosity function that skews heavily toward faint stars. This suggests that Leo A experienced a prolonged period of slow star formation, allowing its stellar population to age and dim over time. On the other hand, dwarf galaxies like IC10, which is undergoing intense star formation, display luminosity functions dominated by bright, massive stars. These contrasting examples highlight the diversity of evolutionary paths that dwarf galaxies can take. The study of luminosity functions in dwarf galaxies also provides clues about the role of dark matter. Since dwarf galaxies are dominated by dark matter, their gravitational pull can influence the distribution of stars and the rate of star formation. By analyzing how luminosity functions vary across different dwarf galaxies, astronomers can infer the distribution and influence of dark matter within these systems. This, in turn, helps refine our understanding of how dark matter shapes galaxies on both small and large scales. Visuals of luminosity function graphs bring these concepts to life, showing the stark differences between typical and unusual distributions. Comparisons between galaxies like Leo A and IC10 illustrate how star formation history and environmental factors can lead to vastly different outcomes. These graphs not only serve as tools for scientific analysis, but also as windows into the dynamic and ever-changing nature of the cosmos. As we conclude our exploration of dwarf galaxies, their unusual luminosity functions remind us of the complexity and diversity of the universe. These small galaxies, often overlooked in favor of their larger counterparts, hold the keys to understanding some of the most fundamental processes in astrophysics. From star formation to dark matter, dwarf galaxies continue to challenge our assumptions and expand our knowledge, proving that even the smallest systems can illuminate the grandest mysteries of the cosmos. Now turning to the conclusion of our journey through the strange and fascinating world of dwarf galaxies, let's take a moment to reflect on the incredible discoveries we've explored. From the missing satellite problem and ultra-diffuse galaxies to the surprising presence of supermassive black holes and galaxies with no dark matter, these small but mighty systems have reshaped our understanding of the cosmos. Each discovery has peeled back another layer of mystery, revealing the intricate processes that govern galaxy formation, star evolution, and the role of dark matter in shaping the universe. Dwarf galaxies, often overshadowed by their larger counterparts, have proven to be cosmic treasure troves. They challenge our assumptions, offering insights into the early universe, the nature of dark matter, and the complex interplay of forces that drive galactic evolution. Whether it's the ghostly glow of ultra-diffuse galaxies, the explosive star formation in tidal dwarfs, or the enigmatic absence of dark matter in some systems, these discoveries remind us that the universe is far more diverse and dynamic than we once imagined. As we wrap up, it's clear that dwarf galaxies are not just small players in the cosmic drama, they are key to unlocking some of the universe's greatest mysteries. They serve as cosmic fossils, preserving clues about the early stages of galaxy formation, and as laboratories for studying dark matter and star formation in ways that larger galaxies cannot. Their strange and varied properties continue to push the boundaries of astrophysics, inspiring new questions and driving the search for answers. Thank you for joining us on this journey through the strange and wonderful world of dwarf galaxies. If you found this exploration as fascinating as we did, don't forget to like, share, and subscribe for more deep dives into the mysteries of the universe. Let us know in the comments which discovery surprised you the most or what other cosmic mysteries you'd like us to explore next. Until then, keep looking up. The universe is full of wonders waiting to be uncovered.